Hello, dear learners. My name is Priscilla Janko. Some people call me Priscilla for so chatted. Once more, please like and share this video, and you're welcome to subscribe to this YouTube channel. If you're interested in a one-on-one online tutorial session, feel free to email me at the address ftpriest@yahoo.ca. Once more, welcome to this presentation. Throughout this presentation, I will guide you through deriving double angle identities. We'll explore the derivation and one application of this derivation. Let's begin this journey into trigonometry. The learning outcome of this session, I will advise you to please pay attention to this. So by the end of the session, you should be able to derive a double angle identity involving sines and cosine, and should be able to use this identity to simplify a given trigonometric expression. Let's dive into the derivation. We want to derive the double angular identity, which states that sine of 2 alpha is equal to 2 sine alpha times cos alpha. In an attempt to achieve this goal, you're advised to recall the compound angle identity that we did prove in one of our previous videos, which states that sine of alpha plus beta is equals to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. Let's call this equation 1. Therefore, we can rewrite sine of 2 alpha as sine alpha plus alpha. We can rewrite this using this first equation as sine alpha times cos alpha plus cos alpha times sine alpha. Let's rewrite this nicely to obtain sine of alpha times cosine of alpha plus sine of alpha times cosine of alpha. This implies we're going to obtain 2 sine alpha cos alpha. End of proof. We have proven that sine 2 alpha is equal to 2 sine alpha times cos alpha. Let's now dive into the derivation of cos 2 alpha. Once more, you have to recall the compound angle identities. So you have to recall that cosine of alpha plus beta is equals to cosine of alpha times cosine of beta minus sine alpha times sine of beta. Therefore, we can write cos 2 alpha as cos alpha plus alpha. We now use our previously proven identity to obtain cos alpha times cos alpha minus sine alpha times sine alpha. This boils down to cos squared alpha minus sine squared alpha. This is the first form of the derivation of cos 2 alpha, which is equal to cos squared alpha minus sine squared alpha. Now, the second form is to rewrite cos 2 alpha given by cos squared alpha minus sine squared alpha. We now know this trigonometric identity, which states that cosine squared of alpha plus sine squared of alpha is equals to 1. From this expression, we obtain that cos squared of alpha can be written as 1 minus sine squared alpha. So we substitute it into this expression here. So this can be written as 1 minus sine squared alpha bracket minus sine squared alpha. If you open up the bracket, we will obtain 1 minus 2 sine squared alpha. The second form states that cosine of 2 alpha is equal to 1 minus cos or 1 minus 2 sine squared alpha. The third form will consist of having this, we have cos 2 alpha is equal to cos squared alpha minus sine squared alpha. The third form now will now consist of using this expression, this trigonometric identity, and rewriting it as sine squared alpha is equal to 1 minus cos squared alpha. We substitute this into this expression to obtain cosine squared alpha minus bracket 1 minus cos squared alpha. If you open up the bracket, we are going to have cosine squared of alpha minus 1 plus cosine squared alpha. And this gives us what? Cos 2 cosine squared of alpha minus 1. Then we are done with the derivation of cos 2 alpha. Take note, derivation of cos 2 alpha has 3 forms that we have mentioned so far. Now, let's look at how we can use this well-known double angle identity to simplify a given trigonometric expression. This is to show you how amazing some trigonometric concepts can be. Let's dive into the illustration. We want to use the left-hand side and apply our well-known double angle identities. The left-hand side states that we have 1 divided by sine 2b minus 1 over tan 2b. This is the same as, remember, we have tan A given by sine A. You all remember this trigonometric identity. We are going to use this. So we're going to have 1 over sine 2b minus 1 over sine 2b over cos 2b. We're now going to obtain 1 over sine 2b. Remember, the reciprocal of this expression becomes, we're going to have minus cos 2b divided by sine 2b. We have a common denominator. We can rewrite this expression as 1 minus cosine of 2b divided by sine 2b. Okay? Our goal is to obtain tan b. Therefore, we can rewrite this expression. We can simplify this using our well-known double angle identities that we've proven in one of our previous slides. So this expression can be written as, so remember from our previous slide, we had 1 minus cosine of 2b over sine 2b. This implies we can write it as 1 minus, we can use our well-known double angle identity, as I did mention so far, to obtain 1 minus 2 sine squared b over 2 sine b cos b. If you open up the brackets, we are going to have 1 minus 1 plus 2 sine squared b over 2 sine b cos b. This cancels, this cancels. What do we obtain? 2 sine squared b over 2 sine b cos b. These two cancels, one sine cancels with the other sine in the denominator, and we are going to have sine b over cos b, and the final outcome is tan b. So always remember where you are heading to and what you have at hand, what double angle identities you can use to be able to simplify a given trigonometric expression. So this is the end of the proof. What have we learned throughout the session? We have learned that sine 2 alpha is equal to 2 sine alpha cos alpha. We have equally learned how to re-express cosine of 2 alpha in 3 different forms. And lastly, after the derivation of these trigonometric double angle identities, we did go through one application, how to use these double angle identities to simplify a given trigonometric expression. This is also the end of this video. Once more, like and subscribe to this. Like this video, share this video, subscribe to this YouTube channel. Thank you. See you in the next upcoming video.